Welcome to Triune Biblical University Global Extension USA channel. A warm welcome to all our returning subscribers and a heartfelt greeting to our new viewers. We're so glad to have you with us today. Whether you've been following us for a while or are just joining the community, we're excited to embark on this learning journey together. At Triune Biblical University Global Extension USA, we strive to provide valuable educational content that empowers you to grow, learn, and succeed. Your continued support and participation mean the world to us. In today's session, we are diving into lecture topic, where we'll explore important concepts and provide practical knowledge that you can apply in real-world scenarios. This lecture is designed to challenge your thinking and deepen your understanding, whether you're a beginner or an advanced learner. Thank you for joining us, and we hope you find today's lecture both insightful and inspiring. Let's get started. Chapter 11: Ground Improvement Techniques. 11.1 Soil Stabilization Methods. Soil stabilization is a key ground improvement technique used in geotechnical engineering to enhance the strength, durability, and workability of soils by modifying the properties of weak or problematic soils. Stabilization methods can make them more suitable for construction purposes. These techniques are crucial in areas with soft, expansive, or loose soils where the soil cannot support the desired loads or is prone to excessive settlement. There are various soil stabilization methods, each with its own set of advantages and specific applications. This section outlines the most common soil stabilization techniques used in geotechnical engineering. 1.1.1 Mechanical stabilization. Mechanical stabilization involves modifying the soil's properties through physical processes that alter its composition and structure. This method is often used to improve the load-bearing capacity and reduce soil movement. 1. Compaction. Compaction is the process of increasing the density of the soil by reducing the voids between soil particles. This is typically achieved by applying mechanical energy through rollers, vibrating plates, or tamping tools. Purpose. The goal is to increase the soil's shear strength and reduce its compressibility. Compaction is often used in the construction of embankments, foundations, and roadways. Applications. Suitable for granular soils like sand, gravel, and crushed stone. 2. Grading. Grading is the process of adjusting the particle size distribution of the soil to optimize its compaction and drainage properties by adding larger particles, such as gravel, or finer materials like clay. The soil can be better compacted and more stable. Purpose. This method helps to improve the soil's overall strength and reduce the risk of settlement. Applications. Common in road construction and base layers for pavements. 3. Vibrocompaction and dynamic compaction. Vibrocompaction involves the use of a vibrator to compact loose sandy soils. The vibration helps to rearrange the soil particles, reducing voids and increasing soil density. O purpose. It enhances the load-bearing capacity of the soil and improves its resistance to liquefaction. O applications. Used in areas with loose sand or granular soils, especially for foundations or infrastructure. 1.1.2 Chemical stabilization. Chemical stabilization involves the use of chemical additives or binders to improve the physical properties of the soil, such as its strength, durability, and resistance to moisture. This technique is often applied to fine-grained soils, such as clays or silts, which are more difficult to compact and stabilize through mechanical means. 1. Cement stabilization. Cement is mixed with the soil to improve its strength, reduce plasticity, and lower its permeability. The process involves adding a specified amount of cement and mixing it with the soil, followed by compaction. O purpose. Cement stabilization improves the shear strength and reduces the swelling and shrinkage behavior of expansive soils. O applications. Used for stabilizing clayey soils, subgrades for roads, and foundation beds for buildings. 2. Lime stabilization. Lime is commonly used to stabilize fine-grained soils, especially clays. It reacts with the clay minerals to form cementitious compounds that improve the soil strength and workability. O purpose. Lime stabilization reduces soil plasticity, improves compaction, and increases shear strength. O applications. Frequently used for road construction, embankments, and in regions with expansive clays. 3. Fly ash stabilization. Fly ash, a byproduct of coal combustion, can be mixed with soil to improve its strength and reduce its permeability. It reacts with the soil to form cementitious compounds that enhance soil stability. O purpose. Fly ash stabilization is cost-effective and environmentally friendly, making it an excellent option for improving soil properties in large-scale infrastructure projects. O applications. Often used for stabilizing silts, clays, and soft organic soils in road construction, embankments, and landfills. 4. Polymer stabilization. Polymers, such as polyurethane, are sometimes used to stabilize soils by creating a chemical bond between soil particles. O purpose. Polymer stabilization improves the durability of the soil and makes it more resistant to water erosion, swelling, and shrinkage. O applications. Commonly used in areas where long-term soil stability is required, such as for highway construction or industrial sites. 5. Bituminous stabilization. Bitumen or asphalt is mixed with soil to improve its resistance to water and its strength. This technique is often used in road construction to create a waterproof and durable base. O purpose. It reduces the soil's permeability and enhances its stability, especially in areas with high moisture content. O applications, typically used for road subgrades and bases, particularly in wet or coastal regions. 1.1.3 Biological stabilization. Biological stabilization methods involve the use of plants or microbial agents to stabilize soil. These methods are environmentally friendly and are gaining popularity for their sustainability and low environmental impact. 1. Phytoremediation. Phytoremediation involves planting vegetation, particularly deep-rooted plants, to improve soil stability. The roots help to bind the soil particles together, reducing erosion and promoting soil structure. Purpose. This method enhances the soil's resistance to erosion, stabilizes slopes, and can also help with the absorption of contaminants from the soil. Applications. Common in areas prone to erosion, such as steep slopes, embankments, and riverbanks. 2. Microbial-induced carbonate precipitation, MICP. MICP is a biotechnological process that uses bacteria to induce the precipitation of calcium carbonate in the soil, thereby improving its strength and stability. Purpose. This method is environmentally friendly and can enhance the shear strength of the soil, making it more resistant to liquefaction, erosion, and settlement. Applications. Useful in strengthening weak soils and improving the foundation of structures in areas where chemical stabilization is not feasible. 1.1.4 Thermal stabilization. Thermal stabilization involves the use of heat to alter the properties of certain soils, particularly those containing expansive clay minerals. By applying heat, the soil's moisture content is reduced, and its physical properties are modified to make it more stable. 1. Electrical resistivity heating. Electrical resistivity heating involves applying an electric current through soil to heat it. This method is used to modify the moisture content and stabilize soils in areas with problematic expansive clays. Purpose. The heat reduces the soil's volume changes and stabilizes its structure. Applications. Common in areas with highly expansive clays or soils prone to significant volume changes with moisture fluctuations. 1.1.5 Grouting techniques. Grouting is the injection of fluid materials, such as cement-based mixtures, into the soil to improve its strength, reduce permeability, and stabilize it for construction. This technique is often used for deep soil improvement or to seal areas with water ingress problems. 1. Cement grouting. Cement grouting involves injecting a cement slurry into the soil to form a solidified mass that increases the soil's strength and reduces its permeability. Purpose. It is used for stabilizing loose soils, reducing groundwater flow, and increasing the load-bearing capacity of the ground. O applications, often used in foundation work, soil consolidation, and sealing. Groundwater flows in tunnels or dams. 2. Chemical grouting. Chemical grouting involves the injection of chemical solutions, such as sodium silicate or polyurethane, into the soil. These chemicals react with the soil to form a gel-like substance that binds soil particles together. Purpose. It enhances soil strength and decreases its permeability, making it more resistant to erosion and settlement. Applications. Useful for stabilizing loose sands, silts, and soft soils, and for controlling groundwater flow in underground structures. Conclusion. Soil stabilization techniques are essential for improving the properties of problematic soils, making them suitable for construction. Each stabilization method, whether mechanical, chemical, biological, thermal, or through grouting, offers unique benefits and applications. The selection of the most appropriate technique depends on factors such as soil type, project requirements, environmental considerations, and cost-effectiveness. With the continuous development of new technologies and materials, the effectiveness and sustainability of soil stabilization methods continue to improve, helping geotechnical engineers design safer and more durable structures. Chapter 11. Ground Improvement Techniques. 11.2 Deep Soil Mixing and Vibrocompaction. Ground improvement techniques such as deep soil mixing and vibrocompaction are critical methods for enhancing the properties of problematic soils. These techniques are typically applied to weak or unstable soils that require significant improvement to support structures or construction projects. Both deep soil mixing and vibrocompaction play a key role in geotechnical engineering, offering solutions to increase soil strength, reduce settlement, and improve overall ground stability. Below, we explore both techniques in detail. 1.2.1 Deep Soil Mixing, DSM. Deep soil mixing, DSM, is a ground improvement technique in which binders, usually cement, lime, or other stabilizing agents, are introduced into the soil at depth by mixing them with the native soil. This process creates a more stable and stronger soil structure, which is suitable for construction purposes. The technique involves the use of specialized equipment to mix soil and binder materials at specific depths, creating improved soil columns or blocks. 1.2.1.1 Process of Deep Soil Mixing. 1. Soil mixing. The process starts with a mixing tool, typically a set of augers or a rotating blade, being driven into the soil at the desired depth. These tools mix the soil with the binder, cement or lime to create a solidified column or block of improved soil. The binder is typically injected in slurry form during the mixing process to ensure uniform distribution. 2. Binder injection. The binder is injected under pressure, ensuring proper mixing and chemical reaction with the soil. Common binders include cement, lime, or a combination of both, depending on the soil type and the required strength. Properties. 3. Columns or slabs formation. The soil and binder mixture creates columns or slabs, also known as soil cement columns, within the soil mass. These columns serve as the improved load-bearing zones that reinforce the overall ground structure. 1.1.2.1.2 Applications of deep soil mixing. Foundation improvement. DSM is particularly useful for improving the bearing capacity of soils for foundations. The process is used for soft soils, loose sands, silts, or highly compressible clays that would otherwise not support heavy structures. The columns formed by deep soil mixing act as reinforcement to distribute loads evenly, reducing the risk of excessive settlement and improving the overall stability of the foundation. Liquefaction mitigation. In regions prone to seismic activity, DSM can be employed to mitigate liquefaction risks. By reinforcing the soil with deep soil mixing columns, the soil's resistance to liquefaction is enhanced, making it more stable during earthquakes. Slope stabilization. DSM is used to stabilize slopes and prevent landslides in areas with weak soils. The deep mixing columns reinforce the soil mass, reducing the risk of slope failure due to increased strength and cohesion. Contaminated soil remediation. DSM is also used in the remediation of contaminated sites. By incorporating stabilizing agents, the technique can reduce the mobility of contaminants in the soil and prevent further spread of pollutants. 1.1.2.1.3 Advantages of deep soil mixing. Improves strength and stability. DSM improves the shear strength and bearing capacity of soils, making them suitable for supporting heavy structures. Reduce settlement. The columns created by DSM help reduce settlement under load, providing a stable foundation. Environmental benefits. DSM can be an environmentally friendly technique, especially when lime or other non-toxic binders are used. It can also be applied in contaminated soil areas to reduce environmental hazards. Versatility. DSM is highly effective in a variety of soil types, including soft clays, silts, and loose sands, which are otherwise challenging to improve using traditional methods. 1.2.2 Vibrocompaction. Vibrocompaction, also known as vibroflotation, is a ground improvement technique used to densify loose granular soils such as sands and gravels. This method uses vibration to rearrange the soil particles, reducing the voids between them and increasing the soil's density. The result is a more stable ground, capable of supporting larger loads and reducing settlement. 11.2.2.1 Process of vibrocompaction. 1. Vibration probe. The process involves a large vibrating probe, often called a vibraflot, being lowered into the ground. The vibraflot produces intense vertical vibrations that penetrate deep into the soil. 2. Soil compaction. As the vibraflot vibrates the soil particles are rearranged and compacted. The process effectively reduces the void ratio between the particles and increases the density of the soil. 3. Soil improvement. The vibraflot is raised in stages while continuing to vibrate the soil, allowing for incremental densification at different levels. In some cases, the process is combined with the injection of water, air, or grout to further improve the soil's characteristics. 4. Completion. Once the compaction process is complete, the vibraflot is removed, and the ground is left with improved density and stability. In some cases, densification may be verified by measuring the soil's relative compaction or by conducting field tests, such as the Standard Penetration Test, SPT, or Cone Penetration Test, CPT. 11.2.2.2 Applications of vibrocompaction. Improvement of loose sands. Vibrocompaction is especially active in improving loose sandy soils that are prone to liquefaction or excessive settlement. By densifying these soils, vibrocompaction increases their load-bearing capacity and makes them more resistant to seismic activity. Prevention of liquefaction. In areas subject to seismic activity, vibrocompaction is used to reduce the risk of liquefaction by densifying loose granular soils, which helps to prevent soil failure during an earthquake. Foundation and roadway construction. Vibrocompaction is widely used in the construction of roads, embankments, and foundations, where dense soils are required to support the weight of structures and vehicles. Reclamation of land. The technique is commonly used in land reclamation projects to improve the stability of sandy soil or reclaimed land, ensuring that it can support future construction. 11.2.2.3 Advantages of vibrocompaction. Increased density and strength. Vibrocompaction significantly increases the density of loose granular soils, thereby improving their strength and stability. Reduce settlement. The technique helps to reduce both immediate and long-term settlement of structures by densifying the soil, making it more resistant to deformation under load. Liquefaction mitigation. By densifying soils, vibrocompaction reduces the risk of liquefaction in areas subject to earthquakes, ensuring safer construction in seismic zones. Cost-effectiveness. Vibrocompaction is often more cost-effective compared to other methods of ground improvement, especially for large-scale projects involving loose, granular soils. Minimal environmental disruption. The process of vibrocompaction generally causes minimal environmental disruption compared to other soil improvement techniques. It is a relatively non-invasive method, and the vibrations can be controlled to minimize the EX on surrounding structures. 1.2.3 Comparison of deep soil mixing and vibrocompaction. Feature deep soil mixing, DSM, vibrocompaction. Soil types. Active for cohesive soils, clays, silts, and granular soils. Primarily used for granular soils, sands, gravels. Applications. Foundation improvement, slope, stabilization, liquefaction mitigation, roadways, embankments, seismic hazard mitigation, improvement, mechanism, soil cement columns formed by mixing binders with native soil, densification of granular soils through vibration, binder material cement, lime, fly ash, etc. No binders used. EECT on soil. Increases shear strength, reduces permeability, prevents settlement, increases soil density, improves load bearing capacity. Environmental impact. Can be environmentally friendly if non-toxic binders are used. Minimal environmental disruption, non-invasive. Depth of treatment. Can treat deep soil layers up to 30 meters or more, typically up to 20 meters. Feature deep soil mixing, DSM, vibrocompaction. Speed of application. Slower process due to mixing and curing time. Faster compared to other techniques. Cost. Can be more expensive due to binder costs and machinery. Generally cost-effective for large-scale projects. Conclusion. Both deep soil mixing, DSM, and vibrocompaction are essential ground improvement techniques that owe unique advantages for enhancing the properties of weak or unstable soils. While DSM is primarily used for improving cohesive soils and providing a solid foundation for structures, vibrocompaction is most effective in densifying loose granular soils, particularly in seismic zones. The choice of technique depends on the soil type, project requirements, and specific ground conditions, and both methods contribute significantly to ensuring the stability, safety, and durability of construction projects. Chapter 11. Ground Improvement Techniques. 11.3 Grouting Techniques in Geotechnical Engineering. Grouting is a ground improvement technique that involves injecting a fluid or semi-fluid material, called grout, into soil or rock formations to enhance their properties. The injected grout fills voids, cracks, and fractures in the soil or rock, improving their strength, stability, permeability, and other geotechnical characteristics. Grouting is widely used in various geotechnical engineering applications, including foundation support, soil stabilization, seepage control, and tunnel construction. In this section, we explore the different types of grouting techniques used in geotechnical engineering, their applications, processes, and advantages. 1.3.1 Types of grouting techniques. Grouting techniques can be classified into various types based on the materials used and the objectives of the process. Below are the main types of grouting techniques commonly used in geotechnical engineering. 1.3.1.1 Permeation grouting. Permeation grouting involves injecting grout into soil to fill the voids and permeate the pore spaces between the soil particles. The goal is to reduce the permeability of the soil or improve its strength and stability by filling the voids with a solidifying grout. Materials used: cement-based grouts, chemical grouts, e.g., sodium silicate, polyurethane. Applications: groundwater control, seepage prevention, foundation strengthening. 1.3.1.2 Compaction grouting. Compaction grouting involves injecting a thick grout mixture into the ground to displace and compact the surrounding soil, thereby increasing its density and improving its load bearing capacity. The grout is injected under pressure, causing the soil particles to shift and compact as the grout displaces the soil. Materials used: cement-based grout with varying degrees of viscosity, low mobility grout. Applications: soil densification in loose or soft soils, stabilization of weak or compressible soils, foundation support for structures. 1.3.1.3 Jet grouting. Jet grouting uses high-pressure grout jets to erode the soil and mix it with the grout, creating solidified soil cement columns. The technique is used to treat deep soils and is effective in both cohesive and non-cohesive soils. Jet grouting can be performed at depths ranging from shallow to very deep levels. Materials used: cement-based grouts, bentonite slurries, chemical additives. Applications: waterproofing and seepage control, soil stabilization, foundation reinforcement, excavation support. 1.3.1.4 Chemical grouting. Chemical grouting involves the injection of chemical solutions that react with the soil or groundwater to form a solid mass or reduce permeability. The chemical grout may harden or bond the soil particles together, increasing the strength and reducing the potential for settlement. Materials used: sodium silicate, polyurethane, acrylics. Applications: seepage control in permeable soils, waterproofing, stabilization of loose soils or fractured rock, mitigation of soil liquefaction. 11.3.1.5 Compaction grouting with superplasticizers. This type of grouting technique involves the injection of highly fluid grout mixtures, including superplasticizers, which help to enhance the grout's flowability and increase the efficiency of the compaction process. Superplasticizers allow the grout to penetrate and compact fine-grained soils, such as silts and clays. Materials used: cement-based grout, superplasticizers, additives for fluidity. Applications: deep compaction of fine-grained soils, enhancement of load-bearing capacity, minimization of soil settlement. 1.3.2 Grouting process. The grouting process typically involves several key steps. 1. Site investigation and design. Detailed geotechnical investigations are conducted to determine the soil properties, groundwater conditions, and other relevant factors. Based on this data, the appropriate grouting technique and grout materials are selected. A grout injection plan is developed to determine the depth, pressure, and grout mix proportions for the injection process. 2. Grout injection. The grout is injected into the ground through a series of boreholes drilled into the soil or rock. The grout is injected under controlled pressure and flow rates, ensuring even distribution throughout the target area. In some cases, a series of injection stages may be used to create overlapping grout columns or continuous grout barriers. 3. Monitoring and quality control. The grouting process is closely monitored to ensure that the grout is being injected at the proper rate and pressure. Various testing methods such as grout injection pressure and volume are used to assess the effectiveness of the grouting process. After grouting, quality control tests such as borehole inspection, permeability tests, and compressive strength tests may be conducted to confirm the improvement in soil properties. 4. Curing and final inspection. After the grout has been injected, it is allowed to cure and harden. Depending on the type of grout used, curing may take from several hours to days. Final inspections are performed to verify the extent of improvement and ensure the desired outcomes, such as reduced permeability or increased strength. 1.3.3 Applications of grouting in geotechnical engineering. Grouting techniques have wide-ranging applications in geotechnical engineering. Some of the key applications include 1.3.3.1 Foundation improvement. Grouting can be used to enhance the load-bearing capacity and reduce the settlement of foundations. It is commonly used for the improvement of weak or unstable soils beneath existing or proposed foundations. Grouting methods such as permeation or compaction. Grouting help increase soil strength, reduce settlement, and prevent structural damage. 1.3.3.2 Groundwater control and seepage prevention. Grouting is often employed in areas with high groundwater levels or water-sensitive soils. It is used to prevent water seepage into excavations, tunnels, or basements, and to create impermeable barriers in dams, levees, or tunnels. Chemical grouting and permeation. Grouting are commonly used to reduce permeability and control groundwater flow. 1.1.3.3.3 Slope stabilization. In unstable slopes or embankments, grouting can be used to increase the strength of the soil or rock, preventing landslides and improving overall slope stability. Grouting is often combined with other slope stabilization techniques such as soil nailing or geogrid reinforcement to enhance the stability of slopes and prevent failure. 1.1.3.3.4 Seismic hazard mitigation. Grouting can be used to mitigate the risk of liquefaction during earthquakes by increasing soil density and reducing permeability. Grouting helps prevent soil failure and ground deformation under seismic loading. This is particularly useful in loose sands or siltous soils that are prone to liquefaction. 1.1.3.3.5 Tunnel and shaft construction. In tunnel and shaft construction, grouting techniques are employed to control water ingress and to stabilize the surrounding soil or rock. Grouting is used to create watertight barriers around the tunnel and to prevent ground movement or settlement that could affect the tunnel structure. Jet grouting is often employed in such applications for deep ground treatment. 1.1.3.3.6 Sinkhole and void remediation. In areas prone to sinkholes or ground subsidence, grouting can be used to fill voids and stabilize the soil. The grout is injected into cavities, fractures, and voids to solidify the ground, preventing further subsidence and potential surface collapse. 1.3.4 Advantages of grouting techniques. Increased strength and stability. Grouting improves the strength of weak soils, making them more stable and capable of supporting heavier loads. Reduce permeability. Grouting helps to decrease the permeability of soil, preventing the infiltration of water into structures or foundations. Cost-effective. Grouting is often a more cost-effective solution than other methods of ground improvement, especially for large areas or sites with complex soil conditions. Minimal disruption. Grouting is typically a non-invasive method that causes minimal disruption to the surface or surrounding structures, making it ideal for urban construction or sensitive environments. Versatility. Grouting techniques can be adapted to a wide range of soil types and project requirements, including those in complex or challenging geotechnical environments. 1.3.5 Limitations of grouting. Soil characteristics. Grouting may not be active in soils with very large voids, highly fractured rock, or highly permeable materials, where grout may not adequately fill all gaps. Cost variability. While generally cost-effective, the cost of grouting can vary. Depending on the depth of injection, type of grout used, and site conditions, it may not always be the most economical option for all types of projects. Time-consuming. Some grouting techniques, particularly chemical grouting or jet grouting, can be time-consuming and require careful monitoring to ensure the desired results are achieved. Conclusion. Grouting is a versatile and effective technique for improving soil properties and ensuring the stability of geotechnical projects. The choice of grouting technique depends on the specific site conditions, soil types, and desired outcomes. Whether used for foundation improvement, seepage control, or soil stabilization, grouting plays a key role in enhancing the safety and performance of construction projects in geotechnical engineering. With proper planning, execution, and monitoring, grouting can be a powerful tool for addressing challenging soil conditions and ensuring the success of various infrastructure projects. Chapter 11. Ground Improvement Techniques. 11.4 Geofoam and Geotextile Applications. Geofoam and geotextiles are important materials used in ground improvement techniques, particularly for lightweight soil stabilization, slope stabilization, and reinforcement in various geotechnical applications. Both materials serve distinct purposes but are often used together to enhance the performance of geotechnical systems in different environments. In this section, we explore the properties, applications, and advantages of geofoam and geotextiles in geotechnical engineering, with a focus on their roles in improving the behavior of soil and facilitating safer, more durable infrastructure. 1.4.1 Geofoam. Properties and applications. Geofoam is a lightweight, rigid foam material made from expanded polystyrene, EPS, or other similar materials. Due to its low density and high compressive strength, geofoam is used to address challenges associated with heavy soils, subsidence, and weak ground conditions. 1.4.1.1 Properties of geofoam. Low density. Geofoam has a density ranging from 15 to 45 kilograms per cubic meter, making it much lighter than conventional soil or other geotechnical materials. Its low weight reduces the load on the underlying soil, making it ideal for projects involving soft or compressible soils. High compressive strength. Despite its lightness, geofoam has a high compressive strength-to-weight ratio, which allows it to support significant loads without deformation. Thermal insulation. Geofoam provides excellent insulation properties, which can be beneficial in projects involving temperature-sensitive materials or underground construction. Water resistance. Geofoam is impervious to water, which makes it suitable for use in drainage-restricted environments. Durability. Geofoam is resistant to chemical degradation ensuring long-term performance in various environmental conditions. 1.4.1.2 Applications of geofoam. 1. Lightweight fill for soil stabilization. Geofoam is widely used as a lightweight fill material to reduce the weight and stress on underlying soft or compressible soils. Its use is particularly advantageous when traditional fill materials would result in excessive settlement or cause damage to existing structures. Example: in areas with soft soils or where ground improvement is difficult, geofoam is used in embankments or road construction to avoid differential settlement. 2. Slope stabilization. In slope stabilization projects, geofoam can be used to reduce the weight of the slope, thus minimizing the risk of landslides or soil erosion. The foam's low density helps to stabilize slopes without adding significant load to the existing soil layers. Example: geofoam is used in the construction of highway embankments, reducing the risk of landslides and providing long-term slope stability. 3. Bridge approach embankments. Geofoam is commonly used in bridge approach embankments, where it minimizes settlement or movement that could otherwise affect the alignment and integrity of the bridge. Its low weight reduces the lateral pressure exerted on the bridge foundation. 4. Seismic applications. In earthquake-prone areas, geofoam helps reduce the impact of seismic forces on structures by minimizing ground shaking and settling, providing a flexible solution for infrastructure projects in such regions. 5. Foundation support. Geofoam can be used as a lightweight, low-settlement material for foundation support, especially in areas where conventional fill materials would lead to excessive settlement. 1.4.2 Geotextiles. Properties and applications. Geotextiles are synthetic materials used in geotechnical engineering to provide a range of functions such as reinforcement, drainage, filtration, and separation of soil layers. These woven or non-woven fabrics are made from polymers like polypropylene, polyester, or polyethylene. 1.4.2.1 Properties of geotextiles. High tensile strength. Geotextiles have excellent tensile strength, allowing them to resist deformation under applied loads. This makes them effective in reinforcing weak soils or providing additional stability to structures. Durability. Geotextiles are resistant to various environmental factors, including UV radiation, chemical degradation, and biological attack, ensuring their long-term functionality in challenging conditions. Permeability. Depending on the type of geotextile, it can either allow water to pass through, permeable, or resist water flow, impermeable. Geotextiles with high permeability are often used in drainage applications. Flexibility. Geotextiles are flexible materials that can conform to the shape of the underlying soil or structure, making them adaptable to a wide range of site conditions. 11.4.2.2 Applications of geotextiles. 1. Soil reinforcement. Geotextiles are commonly used to reinforce weak or loose soils. When placed between soil layers, geotextiles improve the soil's load-bearing capacity by distributing the applied loads and reducing the potential for settlement. Example: geotextiles are used in the construction of retaining walls, embankments, and roadways, providing reinforcement in areas with soft or unstable soil. 2. Separation of soil layers. In applications where two different types of soil must be kept separate to prevent mixing or contamination, geotextiles are used as a separation layer. This ensures the stability of the construction while preserving the integrity of each soil layer. Example: geotextiles are used in road construction to separate the subgrade soil from the base material, preventing mixing and ensuring better load distribution. 3. Drainage and filtration. Geotextiles are highly active in drainage applications, where water flow needs to be controlled or directed. They act as a filter, allowing water to pass through while preventing soil particles from being carried away, thus maintaining the integrity of the soil structure. Example: geotextiles are used in the construction of French drains, stormwater management systems, and retaining walls to facilitate water drainage and prevent soil erosion. 4. Erosion control. In areas prone to soil erosion, geotextiles provide a protective barrier to prevent the loss of soil particles. They are particularly useful in stabilizing slopes, embankments, and coastal areas by reducing the impact of wind and water erosion. Example: geotextiles are used in slope stabilization and shoreline protection projects to reduce the risk of erosion and improve the long-term stability of the site. 5. Landfill lining and covering. Geotextiles are commonly used in landfill construction to separate waste from the surrounding soil, prevent contamination, and facilitate the drainage of leachate. They are also used in covering the landfill to reduce the spread of odors and protect against contamination. Example: in municipal solid waste landfills, geotextiles are employed as a part of the liner system to contain waste and prevent groundwater contamination. 6. Pavement design and repair. Geotextiles are used in pavement applications to reinforce the base and subbase layers, reduce cracking, and improve the overall performance and lifespan of the pavement structure. Example: geotextiles are placed between the subgrade and base course in road construction to improve pavement strength and reduce deformation. 1.4.3 Combined use of geofoam and geotextiles. Geofoam and geotextiles are often used together in ground improvement projects to maximize their benefits. The combination of these materials can provide a more effective solution to address a range of geotechnical challenges. 1. Stabilization of embankments. In embankment construction, geofoam can be used to reduce the weight on the underlying soil, while geotextiles provide reinforcement and prevent soil mixing. The combination helps to ensure long-term stability and prevent settlement. 2. Slope protection. Both geofoam and geotextiles are used in slope protection. Applications. Geofoam reduces the weight on the slope, while geotextiles provide reinforcement and filtration, ensuring that water is effectively drained away and preventing soil erosion. 3. Drainage systems. In drainage applications, geofoam can be used to fill in voids or provide insulation, while geotextiles act as a filtration medium. This combination improves water flow and helps protect the surrounding soil from erosion or contamination. 1.4.4 Advantages of geofoam and geotextiles. Improves soil stability. Both geofoam and geotextiles contribute to the stabilization of soft, loose, or unstable soils by enhancing soil properties and preventing excessive settlement. Cost-effectiveness. The use of geofoam and geotextiles can reduce the need for expensive ground improvement methods, such as soil replacement or deep foundation systems, making these materials an economical choice for many applications. Reduced environmental impact. Both geofoam and geotextiles are lightweight materials that can reduce the need for heavy machinery and minimize disturbance to the environment during installation. Versatility. Geofoam and geotextiles can be used in a wide variety of geotechnical applications, including embankments, slopes, pavements, drainage systems, and foundation support. Conclusion. Geofoam and geotextiles are versatile and effective materials used in ground improvement techniques. Geofoam's lightweight and compressive strength make it an ideal material for reducing the load on weak soils, while geotextiles serve a wide range of functions, including reinforcement, filtration, and drainage. Together, these materials can improve soil stability, reduce environmental impacts, and provide cost-effective solutions for a wide variety of geotechnical applications. The combined use of geofoam and geotextiles is an essential aspect of modern geotechnical engineering, helping to ensure the success of infrastructure projects in diverse environments. Chapter 11. Ground Improvement Techniques. 11.5 Advances in Ground Improvement Technologies. Ground improvement techniques have significantly evolved over the years, driven by the increasing demand for more efficient, cost-effective, and sustainable solutions in geotechnical engineering. Advances in material science, construction techniques, and technology have expanded the range of methods available for improving the properties of soils, stabilizing weak or problematic ground, and enabling the safe construction of infrastructure in challenging environments. In this section, we discuss the latest advancements in ground improvement technologies, including innovative methods, tools, and materials that are transforming the field of geotechnical engineering. 1.5.1 Advances in Soil Stabilization Methods. Soil stabilization methods have seen significant technological advancements, owing more efficient and environmentally friendly ways to improve soil properties. Modern stabilization techniques not only enhance the mechanical strength of soil, but also address issues like environmental sustainability and cost-effectiveness. 1.5.1.1 Use of geopolymers and sustainable binders. Geopolymers and sustainable binders, such as fly ash, slag, and natural podzolans, are gaining popularity as alternatives to traditional cement for stabilizing soils. These materials have lower carbon footprints and similar, if not superior, strength characteristics compared to conventional stabilization methods. Geopolymer stabilization. Geopolymers are made from industrial byproducts like fly ash or slag mixed with alkali activators. These materials form strong, durable bonds when mixed with soil, improving its load-bearing capacity and reducing its susceptibility to water erosion. Sustainable binders, incorporating industrial waste materials in soil stabilization, such as fly ash or cement kiln dust, reduces the environmental impact of construction projects and provides an eco-friendly solution to soil improvement. 1.5.1.2 Nanotechnology in soil stabilization. Nanotechnology has brought about innovations in soil stabilization by introducing nanoparticles into soil matrices. These nanoparticles can enhance soil structure, increase its strength, and reduce permeability. Nanosilica and nanoclay materials, for example, have been shown to significantly improve the mechanical properties of soil when applied at small dosages. Nanosilica stabilization. When mixed with soil, nanosilica particles fill in the micropores of soil grains, increasing the cohesion and strength of the soil. Nanoclay stabilization. Nanoclay particles improve the cohesion and overall stability of fine-grained soils, owing potential solutions for foundation engineering in weak or problematic soil conditions. 1.5.2 Deep soil mixing and vibrocompaction. 1.5.2.1 Innovations in deep soil mixing (DSM). Deep soil mixing (DSM) is an advanced technique for improving the strength and steadiness of weak soils by mixing them with binding agents such as cement or lime at greater depths. Recent innovations in DSM focus on improving the efficiency and precision of this method, making it applicable to a wider range of soil types and depths. Automated and precision DSM. New automated DSM systems enable greater precision in the mixing process, improving the homogeneity of the soil cement columns and enhancing the overall performance of the technique. Hybrid DSM techniques. Combining DSM with other techniques, such as jet grouting or soil nailing, results in hybrid systems that can achieve superior soil improvement, especially in challenging or non-uniform soil conditions. 1.5.2.2 Vibrocompaction advancements. Vibrocompaction is used to densify loose or granular soils, improving their bearing capacity and reducing settlement. Recent advances in vibrocompaction technologies include high-efficiency vibroflotation, the introduction of high-efficiency vibroflotation equipment has improved compaction depth and reduced energy consumption, making it possible to treat deeper layers of soil with fewer resources. Vibro replacement with geosynthetic reinforcement, integrating geosynthetics with vibro replacement techniques has improved the effectiveness of deep foundations by providing additional reinforcement to the treated soils, making them more resistant to settlement under loading. 1.5.3 Ground freezing and thermally induced ground improvement. Ground freezing is a technique that temporarily solidifies soil by lowering its temperature, creating a frozen barrier that can provide support during excavation or construction. Recent advancements in ground freezing techniques focus on reducing energy consumption and enhancing the speed and reliability of the freezing process. 1.5.3.1 Energy efficient ground freezing systems. Innovative ground freezing systems now use more energy-efficient refrigeration methods, reducing the overall carbon footprint of the process. Additionally, the use of liquid nitrogen and carbon dioxide has improved the speed at which freezing can be achieved, making it a more viable solution for urban projects or areas with sensitive ecosystems. Closed-loop freezing systems. Advances in closed-loop freezing systems allow for the reuse of refrigerants and cooling fluids, resulting in more efficient and sustainable ground freezing processes. 1.5.3.2 Thermally induced ground improvement. Another exciting development is the use of thermal methods for soil improvement. By introducing heat into the ground, certain soil properties can be modified to achieve more favorable engineering conditions. Thermal treatment of expansive soils. Heating expansive soils can reduce their swelling potential and improve their stability, offering a promising solution for foundations in clayey soils prone to volume changes. Thermally assisted ground improvement. This technique is combined with other methods like grouting or compaction to accelerate soil stabilization, particularly in challenging conditions where conventional techniques may be inefficient. 1.5.4 Geosynthetic reinforcement and composite systems. 1.5.4.1 Advanced geosynthetic materials. Geosynthetics, which include geotextiles, geogrids, geocells, and geomembranes, have seen significant advancements in material properties and applications. Modern geosynthetics are designed with improved durability, load-bearing capacity, and flexibility, making them even more effective in ground improvement projects. High-strength geogrids and geotextiles. The development of high-strength, thermally stable geosynthetics has enhanced their performance in soil reinforcement, especially in retaining walls, embankments, and foundations. Composite geosynthetic systems, combining different geosynthetic materials, such as geotextiles with geogrids or geomembranes, has resulted in composite systems that deliver superior soil stabilization, drainage, and filtration properties. 1.5.4.2 Geocell Reinforcement Technology. Geocells, a type of 3D honeycomb-shaped geosynthetic material, are increasingly used for soil stabilization, slope reinforcement, and erosion control. Advances in geocell technology have improved their flexibility, strength, and ease of installation. High-strength geocells. Recent developments in high-strength polymer materials have made geocells more durable and capable of withstanding heavy loads, increasing their use in a wide range of ground improvement applications. Geocell-enhanced pavement systems. Geocells are being integrated into pavement systems to improve load distribution and prevent cracking, especially in areas with poor soil conditions. 1.5.5 Remote sensing and monitoring in ground improvement. The use of advanced remote sensing technologies and monitoring tools has revolutionized the field of ground improvement by providing real-time data on soil behavior, material properties, and the effectiveness of improvement methods. 1.5.5.1 Geophysical monitoring techniques. Innovative geophysical methods, such as ground-penetrating radar, GPR, and electrical resistivity tomography, ERT, are increasingly being used to monitor the effects of ground improvement techniques in real time. These methods provide detailed insights into the soil structure, allowing engineers to assess the effectiveness of treatments and make adjustments as needed. Real-time monitoring. Advanced monitoring systems that integrate sensors, data acquisition systems, and remote sensing technology allow for continuous tracking of soil conditions, helping to detect any changes or failures in ground improvement systems. In situ testing innovations. Modern in situ testing techniques, such as cone penetration testing, CPT, and pressure meter tests, provide real-time data on the behavior of soils under various loading conditions, helping engineers to refine their ground improvement strategies. Conclusion. Advancements in ground improvement technologies are transforming the landscape of geotechnical engineering, from sustainable soil stabilization methods to cutting-edge geosynthetic applications and innovative monitoring techniques. These technologies are enabling more efficient, reliable, and environmentally friendly solutions for addressing complex geotechnical challenges. By leveraging these advancements, engineers can provide more effective ground improvement strategies that ensure the stability and sustainability of infrastructure projects worldwide. As these technologies continue to evolve, they will play a critical role in shaping the future of geotechnical engineering. Chapter 12: Geoenvironmental Engineering. 12.1 Soil Contamination and Remediation. Soil contamination is a critical issue in geoenvironmental engineering that has wide-ranging implications for public health, environmental quality, and the sustainability of construction projects. Contaminants, including heavy metals, hydrocarbons, pesticides, and industrial chemicals, can pose significant threats to ecosystems and human populations if left unaddressed. Understanding the causes, types, and consequences of soil contamination, as well as implementing effective remediation strategies, is a fundamental aspect of geoenvironmental engineering. In this section, we explore the key concepts related to soil contamination, the sources of contaminants, the effects on the environment, and the various techniques available for remediation and soil restoration. 2.1.1 Sources of soil contamination. Soil contamination typically arises from human activities that introduce hazardous substances into the soil. These contaminants can be either organic or inorganic and vary in their toxicity, persistence, and mobility. The primary sources of soil contamination include 2.1.1.1 Industrial and agricultural activities. Industrial waste disposal. Industrial operations, such as mining, manufacturing, and chemical production, often release toxic substances like heavy metals, solvents, and petroleum products into the soil. Improper disposal of waste materials can lead to long-term contamination of soil and groundwater. Agricultural runoff. The use of pesticides, herbicides, and fertilizers in agriculture can result in the contamination of soil through runoff. Overuse of these chemicals can introduce harmful substances like nitrates, phosphates, and persistent organic pollutants (POPs) into the soil, affecting soil health and groundwater quality. 2.1.1.2 Landfills and waste disposal sites. Landfills and waste disposal sites are major sources of soil contamination. Leachate from landfills, which may contain a mixture of hazardous chemicals, can infiltrate the soil, leading to contamination. Additionally, improper disposal of household waste, hazardous materials, and construction debris can introduce dangerous substances into the soil. 2.1.1.3 Oil spills and petrochemical releases. Oil spills, either from transportation, pipeline leaks, or industrial accidents, can contaminate large areas of soil with hydrocarbons. The persistence of these pollutants in Soil often requires long-term remediation to restore soil quality and mitigate environmental damage. 12.1.1.4 Urban and construction activities. Urbanization, including construction activities, excavation, and demolition, can expose contaminated soil to the surface, making it easier for pollutants to spread. These activities can release materials like asbestos, lead, and other hazardous substances into the environment, leading to soil contamination. 2.1.2 Types of soil contaminants. Contaminants in soil can be classified into various categories based on their chemical properties, toxicity, and potential for harm. Common types of soil contaminants include 2.1.2.1 Heavy metals. Heavy metals such as lead, Pb, arsenic, As, cadmium, Cd, mercury, Hg, and chromium, Cr, are among the most concerning soil contaminants due to their toxicity, persistence, and bioaccumulation in the food chain. These metals can come from industrial waste, mining operations, and the use of pesticides and fertilizers. Health impacts. Heavy metal contamination can result in various health problems, including neurological disorders, cancer, and organ damage, especially when they accumulate in human bodies through the consumption of contaminated crops or drinking water. 2.1.2.2 Organic contaminants. Organic contaminants, such as petroleum hydrocarbons, chlorinated solvents, pesticides, and polychlorinated biphenyls, PCBs, are often introduced into the soil through industrial and agricultural activities. Environmental impact. These contaminants can have severe effects on ecosystems, including toxicity to plants and animals. Organic pollutants. Particularly persistent organic pollutants, POPs, can remain in the soil for long periods, posing long-term threats to the environment. 2.1.2.3 Volatile organic compounds, VCs. VCs, including benzene, toluene, and xylene, are chemicals that easily evaporate into the air and contaminate soil. These compounds are commonly found in industrial and petroleum-related activities, and their presence in soil can lead to both soil and air pollution. Health risks. VOCs are often carcinogenic and can cause respiratory issues, headaches, and other health problems when inhaled or ingested. 2.1.2.4 Radioactive materials. Radioactive contaminants, such as uranium and radon, can also affect soil quality. These contaminants are typically associated with mining operations, nuclear power plants, and military activities. Public health concerns. Exposure to radioactive materials can lead to serious health issues, including cancer and genetic mutations, due to radiation exposure. 2.1.3 Effects of soil contamination. The effects of soil contamination are wide-ranging and can have significant environmental, economic, and health impacts. 12.1.3.1 Environmental impact. Degradation of soil quality. Contaminants can alter the physical and chemical properties of the soil, reducing its fertility, water retention capacity, and ability to support plant life. This degradation affects agricultural productivity and biodiversity. Water pollution. Contaminants from soil can leach into groundwater or be carried away by surface runoff, leading to water pollution. This can affect drinking water supplies, aquatic ecosystems, and wildlife. Loss of biodiversity. Contaminated soil can create toxic environments for plants, animals, and microorganisms, leading to a reduction in biodiversity and ecosystem function. 12.1.3.2 Human health risks. Direct exposure. People who work on or live near contaminated sites are at risk of direct exposure to harmful substances, either through inhalation, ingestion, or skin contact. This exposure can lead to acute or chronic health conditions. Food chain contamination. Soil contaminants can be absorbed by plants and enter the food chain. This bioaccumulation can result in human exposure through the consumption of contaminated crops or livestock. 12.1.4 Remediation techniques for soil contamination. Soil remediation refers to the process of cleaning or treating contaminated soil to restore its natural properties and make it suitable for safe use. Several techniques are available for soil remediation, ranging from physical and chemical methods to biological treatments. 12.1.4.1 Bioremediation. Bioremediation is a process that uses microorganisms to degrade organic contaminants in the soil. This method is cost-effective, environmentally friendly, and can be applied to a wide range of organic contaminants. In situ bioremediation. This method involves the treatment of contaminated soil without removing it from its location, using microbial agents, nutrients, or oxygen to promote the natural breakdown of pollutants. Ex situ bioremediation. Contaminated soil is excavated and treated in specialized bioreactors or treatment facilities, where conditions are optimized for microbial degradation. 12.1.4.2 Chemical remediation. Chemical methods involve the use of chemical agents to neutralize or transform contaminants in the soil. Some common chemical remediation techniques include soil washing. This involves washing the soil with a solvent or surfactant to remove contaminants, especially heavy metals and organic compounds. Chemical oxidation. Chemical oxidants, such as hydrogen peroxide or potassium permanganate, are used to break down organic contaminants into non-toxic byproducts. 12.1.4.3 Physical remediation. Physical remediation methods focus on removing or immobilizing contaminants from the soil through physical processes. Soil excavation and disposal. Contaminated soil is physically removed and disposed of at a regulated landfill or treatment facility. Thermal treatment. Soil is heated to high temperatures to vaporize or decompose organic contaminants. This method is effective for volatile compounds such as petroleum hydrocarbons and VCs. 12.1.4.4 Phytoremediation. Phytoremediation uses plants to remove, stabilize, or degrade contaminants in the soil. Certain plants, known as hyperaccumulators, have the ability to absorb heavy metals and other pollutants from the soil. Phytoextraction. Plants absorb contaminants through their roots and accumulate them in their tissues. The plants can then be harvested and disposed of or treated. Phytostabilization. Plants are used to immobilize contaminants in the soil, preventing them from leaching into groundwater or spreading. 12.1.4.5 Stabilization and solidification. In some cases, contaminants can be immobilized in the soil through stabilization and solidification techniques. These methods involve mixing the contaminated soil with binding agents, such as cement or lime, to reduce the mobility of the contaminants and prevent further environmental spread. Conclusion. Soil contamination is a significant concern in geoenvironmental engineering, with far-reaching consequences for human health, ecosystems, and infrastructure. Understanding the sources, types, and impacts of soil contamination is crucial for effective environmental management and remediation. The development of advanced remediation techniques, such as bioremediation, chemical treatments, and phytoremediation, offers promising solutions for mitigating contamination and restoring the integrity of the soil. As technology continues to advance, geoenvironmental engineers will play a vital role in addressing soil contamination challenges and protecting the environment for future generations. Chapter 12. Geoenvironmental Engineering. 12.2 Waste Disposal and Groundwater Protection. Waste disposal and groundwater protection are fundamental components of geoenvironmental engineering. Improper waste disposal practices can lead to soil and groundwater contamination, posing significant risks to human health, the environment, and ecosystems. Groundwater, often a primary source of drinking water, is particularly vulnerable to contamination from various waste disposal activities, such as landfills, industrial waste, and hazardous material spills. This section delves into the principles and practices surrounding waste disposal, focusing on the impact of waste on groundwater and the measures and technologies employed to protect and remediate groundwater resources. 2.2.1 Types of waste and their impact on groundwater. Waste can be categorized based on its origin, composition, and environmental impact. The disposal of different types of waste can lead to contamination of groundwater either through leachate migration or chemical spills. 12.2.1.1 Solid waste. Solid waste includes municipal waste, e.g., household trash, construction debris, industrial waste, and hazardous waste. Landfills, both open and controlled, are the most common means of disposal. However, if improperly managed, landfills can pose serious threats to groundwater due to the leaching of hazardous substances. Leachate formation. Leachate is the liquid that forms when water infiltrates solid waste. This liquid can contain a mix of hazardous chemicals, including heavy metals, organic compounds, and pathogens. If not properly contained, leachate can percolate through the landfill liner and contaminate surrounding groundwater. Groundwater contamination. Contaminants like heavy metals, solvents, and chlorinated compounds can migrate from landfill sites into the groundwater, causing long-term contamination. In some cases, the contaminant plume may spread over a wide area, impacting drinking water supplies. 12.2.1.2 Hazardous waste. Hazardous waste is defined by its potential to cause harm to human health or the environment. It includes substances such as chemicals, solvents, pesticides, and waste from industrial processes. Improper disposal of hazardous waste can lead to soil and groundwater contamination. Contamination pathways. Hazardous waste may leach into the ground, and if stored in open or unregulated conditions, chemicals can enter nearby groundwater supplies. Heavy metals like lead, arsenic, and mercury, as well as toxic organic compounds, are common groundwater contaminants from hazardous waste. Disposal. 12.2.1.3 Wastewater disposal. Wastewater from households, industries, and sewage treatment plants is often discharged into the ground or treated in facilities designed to handle wastewater. If wastewater is improperly disposed of, it can carry pollutants like pathogens, nutrients, and heavy metals into the soil and groundwater. Septic systems. In rural areas, septic systems are commonly used for wastewater disposal. These systems can lead to contamination if not properly maintained. Overflowing or leaking septic tanks can result in the introduction of fecal coliform bacteria, nitrates, and phosphates into groundwater. 12.2.2 Mechanisms of groundwater contamination. Understanding how contaminants move from the point of disposal into groundwater is crucial for mitigating their impact. Several mechanisms drive the movement of pollutants into groundwater. 12.2.2.1 Leaching. Leaching occurs when water percolates through the waste material, dissolving and transporting contaminants. This process is influenced by factors such as the permeability of the soil, the type of waste, and the amount of rainfall or infiltration. Leachate migration. In landfills, leachate can move downward through the waste and the soil, eventually reaching the groundwater. Leachate may contain dissolved chemicals and metals that pose serious risks to groundwater quality. 12.2.2.2 Chemical adsorption and desorption. Some contaminants, particularly heavy metals, can bind to soil particles through a process called adsorption. However, under certain conditions, these adsorbed contaminants can detach from the soil particles and migrate into the groundwater. Adsorption/desorption. The movement of contaminants in groundwater depends on the ability of the soil to adsorb or bind certain chemicals. For example, clay. Particles can adsorb contaminants, but during periods of high moisture or changes in pH, these contaminants may adsorb and enter groundwater. 12.2.2.3 Diffusion. Diffusion refers to the movement of contaminants from areas of high concentration to areas of low concentration. This mechanism is especially important for volatile compounds and organic pollutants, which can be used through the soil and contaminate groundwater over time. 12.2.2.4 Groundwater flow. Groundwater flows through aquifers and other underground water systems. Once contaminants reach an aquifer, they may spread through the groundwater system, potentially affecting large areas and multiple wells. Plume migration. As groundwater moves, contaminants can form a plume that spreads through the subsurface, depending on the flow rate of the groundwater. These plumes can travel significant distances, contaminating wells and water supplies. 12.2.3 Waste disposal methods and groundwater protection. To minimize the risk of groundwater contamination, effective waste disposal methods and protection measures must be employed. This section discusses the strategies used in landfills, wastewater treatment, and hazardous waste management to prevent groundwater pollution. 12.2.3.1 Sanitary landfills and leachate management. Modern landfills are designed to minimize groundwater contamination through a combination of liners, leachate collection systems, and monitoring programs. Landfill liners. Liners made of synthetic materials or clay are used to contain the waste and prevent leachate from migrating into the surrounding soil and groundwater. These liners are designed to be impermeable to liquids and are essential for minimizing the risk of groundwater contamination. Leachate collection systems. These systems collect leachate formed within the landfill and direct it to treatment facilities. Proper treatment of leachate is essential for reducing the risk of groundwater contamination. Groundwater monitoring. Routine groundwater monitoring around landfill sites helps detect any contamination early. Monitoring wells are placed around the site to measure groundwater quality and ensure that contaminants are not escaping into the surrounding environment. 12.2.3.2 Wastewater treatment and disposal. The safe disposal of wastewater requires proper treatment and disposal methods to prevent contamination of groundwater. Septic systems. For rural and suburban areas, maintaining septic systems is crucial to avoid the introduction of pathogens and chemicals into groundwater. Proper design, regular maintenance, and periodic inspection are essential to the safe operation of these systems. Constructed wetlands and natural filtration, in some cases, constructed wetlands and natural filtration systems are used to treat wastewater before it is discharged into the environment. These systems help filter out pollutants and reduce the risk of contamination to groundwater. 12.2.3.3 Hazardous waste management. Disposing of hazardous waste requires specialized handling to prevent contamination. Techniques include secured landfills. Hazardous waste is often disposed of in specially designed secure landfills that include multiple layers of containment, such as clay synthetic liners and leachate collection systems. Deep well injection. In some cases, hazardous liquid waste is injected deep underground into geologically stable formations. This method, known as deep well injection, is used for highly toxic or radioactive waste. It is carefully monitored to ensure that the injected waste does not contaminate groundwater. Treatment and recycling. Hazardous waste may be treated to neutralize harmful components or recycled for reuse in industrial processes. This reduces the need for disposal and mitigates the potential environmental impact. 12.2.4 Groundwater Protection Regulations and Standards. Governments and environmental agencies have established a range of regulations to ensure the protection of groundwater resources. 12.2.4.1 Safe Drinking Water Act, SCWA. The SCWA regulates the quality of public drinking water in the United States, setting standards for the concentration of contaminants in water sources, including groundwater. Under this act, the Environmental Protection Agency, EPA, sets maximum contaminant levels, MCLs, for various pollutants. 12.2.4.2 Resource Conservation and Recovery Act, RCRA. The RCRA governs the disposal of hazardous waste in the U.S. and requires that hazardous waste be treated, stored, and disposed of in a manner that prevents contamination of the environment, including groundwater. The Act mandates rigorous monitoring and reporting to ensure compliance. 12.2.4.3 International Regulations. Internationally, there are a range of conventions and agreements governing groundwater protection, including the European Union Water Framework Directive, which sets standards for water quality and integrates groundwater protection into broader environmental management. Conclusion. Waste disposal and groundwater protection are critical aspects of geoenvironmental engineering that involve the careful management of waste materials to prevent contamination. Proper disposal techniques, such as sanitary landfills, wastewater treatment, and hazardous waste management, play a vital role in minimizing the risk of groundwater pollution. Additionally, ongoing monitoring and regulation are essential to ensure that these practices are effective and that the health of our groundwater resources is maintained for future generations. As global populations grow and industrial activities increase, the importance of sustainable waste disposal and groundwater protection continues to rise. Chapter 12: Geoenvironmental Engineering. 12.3 Environmental Impact of Geotechnical Projects. Geotechnical projects, such as the construction of foundations, tunnels, dams, and roads, can have significant environmental impacts. These projects often require the alteration of natural landscapes and the modification of existing soil, rock, and groundwater conditions, which can lead to both short and long-term environmental effects. Understanding and mitigating these impacts is crucial for ensuring the sustainability and safety of geotechnical engineering projects. This section discusses the potential environmental impacts of geotechnical projects, including soil erosion, groundwater contamination, habitat destruction, and landscape alteration, and outlines the strategies used to minimize and mitigate these effects. 2.3.1 Types of environmental impacts in geotechnical projects. Geotechnical engineering projects can affect the environment in a variety of ways, depending on the type and scale of the project. These impacts can be classified into several categories, including physical, chemical, and biological effects on the environment. 2.3.1.1 Soil erosion and sedimentation. Soil erosion is one of the most common environmental issues associated with geotechnical projects, especially in areas where excavation, grading, and construction activities disturb the natural soil cover. Erosion occurs when loose soil is carried away by wind or water, leading to sedimentation in nearby water bodies. Causes of erosion: activities such as excavation, grading, and the removal of vegetation can increase soil erosion by disturbing the natural soil structure and reducing the land's ability to retain moisture and nutrients. Heavy construction equipment can also compress the soil, reducing its permeability and promoting runoff. Impacts of erosion: erosion leads to the loss of valuable topsoil, which can affect agriculture and plant growth. Sedimentation in rivers and lakes can degrade water quality, disrupt aquatic ecosystems, and reduce the capacity of water storage. Reservoirs. 2.3.1.2 Groundwater contamination. Geotechnical projects that involve drilling, excavation, or excavation-related activities can. ECT groundwater quality. In particular, activities such as landfill construction, mining, and drilling for foundations can lead to contamination of groundwater resources. Sources of contamination: hazardous substances used in construction such as oils, solvents, and chemicals can leach into the soil and migrate into groundwater. The disturbance of contaminated soils during construction can also release pollutants into the water table. Impacts on groundwater. Groundwater contamination can ECT drinking water supplies, disrupt irrigation systems, and harm ecosystems that depend on underground water sources. Contaminants such as heavy metals, pesticides, and hydrocarbons can pose significant risks to human health and the environment. 12.3.1.3 Habitat destruction and loss of biodiversity. Geotechnical projects, especially large-scale construction projects, can lead to the destruction of natural habitats, displacing wildlife and reducing biodiversity in the area. Activities such as deforestation, land grading, and the creation of access roads often involve clearing large areas of land. Habitat fragmentation. Geotechnical projects can fragment natural habitats, making it difficult for wildlife to find food, shelter, and breeding grounds. 4. Example: the construction of highways or dams can isolate animal populations and prevent them from migrating or interacting with other populations. Loss of ecosystem services. The destruction of wetlands, forests, and other ecosystems can reduce the natural services provided by these environments, such as water filtration, carbon sequestration, and soil stabilization. This loss can have cascading effects on local and global ecosystems. 12.3.1.4 Alteration of hydrological systems. Many geotechnical projects alter the natural hydrological conditions of an area, particularly those involving the construction of dams, reservoirs, or tunnels. These alterations can lead to changes in water flow, drainage patterns, and flood regimes. Changes in water flow. Dams and reservoirs can change the natural flow of rivers and streams, affecting the water availability downstream. These changes can impact agricultural activities, drinking water supplies, and aquatic ecosystems. Flooding and erosion. The modification of natural drainage patterns can lead to localized flooding or erosion, particularly in areas where natural flood control mechanisms, such as wetlands, have been disturbed. In some cases, altered water flows can lead to the exacerbation of flood risks in nearby areas. 12.3.1.5 Emissions and air quality impacts. Construction activities associated with geotechnical engineering projects can result in air pollution from the release of dust, diesel exhaust fumes, and other emissions from construction equipment. Dust emissions. excavation, grading, and material handling activities can generate dust that may affect air quality, leading to respiratory problems for workers and nearby residents. Diesel and vehicle emissions. The use of heavy machinery powered by diesel engines can contribute to the release of carbon dioxide, CO2, nitrogen oxides, NOx, particulate matter, and other pollutants that contribute to global warming and local air quality issues. 12.3.1.6 Noise pollution. Construction projects often involve heavy machinery and equipment that produce high levels of noise, which can disturb nearby communities, wildlife, and the natural environment. Impact on wildlife. Loud noises can disturb wildlife populations, leading to stress, disruption of breeding activities, and displacement from natural habitats. Birds and other animals may avoid areas with high noise levels, reducing their ability to find food and mates. Impact on human health. Excessive noise can have detrimental effects on human health, including hearing loss, stress, sleep disturbances, and increased risk of cardiovascular diseases. 2.3.2 Strategies to mitigate environmental impacts. Given the potential environmental risks associated with geotechnical projects, engineers and environmental professionals implement various strategies to minimize these impacts and ensure that projects are completed in an environmentally responsible manner. 12.3.2.1 Environmental Impact Assessments (EIAs). Before beginning any large geotechnical project, it is essential to conduct an environmental impact assessment (EIA). This assessment evaluates the potential environmental impacts of a project and provides recommendations for mitigating negative effects. Risk identification. EIAs identify potential risks, such as habitat destruction, soil erosion, and groundwater contamination, and recommend specific actions to reduce these risks. Mitigation strategies. EIAs provide a detailed plan for mitigating the impacts of the project, including measures like erosion control, water treatment systems, and habitat restoration. 12.3.2.2 Sustainable Design and Construction Practices. Geotechnical engineers use sustainable practices to reduce the environmental footprint of construction activities. These practices may include minimizing soil disturbance, reducing the extent of excavation and grading using erosion control techniques like silt fences and sediment traps, and revegetating disturbed areas to prevent soil erosion. Water management. Using stormwater management systems to control runoff and reduce the risk of contamination of local water bodies. Techniques such as rainwater harvesting, permeable pavements, and green infrastructure can reduce the impact of construction on hydrological systems. Recycling and reuse of materials. Incorporating recycled materials into construction, e.g., crushed concrete, recycled steel, and reusing excavation materials to reduce waste and conserve natural resources. 12.3.2.3 Habitat Restoration and Wildlife Protection. In cases where geotechnical projects ECT natural habitats, it is crucial to implement habitat restoration and wildlife protection measures. These can include wildlife corridors, creating pathways or bridges that allow animals to safely cross. Construction sites, reducing habitat fragmentation and ensuring continued movement between habitats. Restoring disturbed ecosystems. After construction is complete, restoration. EORTs can include planting native vegetation, reintroducing wildlife, and rehabilitating wetlands and other ecosystems impacted by the project. 12.3.2.4 Groundwater Protection Measures. To prevent groundwater contamination, geotechnical engineers use a variety of techniques. Sealing leachate in landfill projects using impermeable liners and leachate. Collection systems to prevent hazardous waste from contaminating groundwater. Monitoring wells. Installing monitoring wells around construction sites and landfills to detect any groundwater contamination early and implement corrective actions as needed. Protective barriers. Using protective barriers and barriers for hazardous materials that could leach into groundwater during construction. 12.3.2.5 Noise and air quality control. To mitigate the impact of noise and air pollution, geotechnical engineers use various strategies. Noise barriers. Installing physical barriers, such as sound walls or tree barriers, to reduce noise levels in residential areas. Dust control. Using water sprays, dust suppressants, and other methods to minimize dust generation during excavation and grading. Emission reductions. Employing cleaner technologies and equipment such as electric-powered machinery or retrofitting older diesel engines with cleaner emission technology to reduce pollution levels. Conclusion. Geotechnical projects, while necessary for infrastructure development, can have significant environmental impacts. Understanding these impacts and implementing strategies to mitigate them is essential for ensuring the sustainability and safety of these projects. Through careful planning, environmental assessments, and the adoption of best practices in construction and design, engineers can minimize the environmental footprint of geotechnical projects and contribute to the protection of natural resources and ecosystems. Chapter 12. Geoenvironmental Engineering. 12.4 Geoenvironmental Risk Assessment Models. Geoenvironmental risk assessment is a critical process in understanding and managing the potential impacts of geotechnical and environmental hazards. This process involves evaluating the risks associated with soil contamination, groundwater pollution, landslides, waste disposal, and other geoenvironmental issues. Geoenvironmental risk assessment. Models are designed to predict, evaluate, and manage the potential environmental impacts, thus helping engineers, planners, and environmentalists develop effective mitigation strategies. This section discusses the various models and approaches used in geoenvironmental risk assessments, their applications, and the tools available for understanding and managing geoenvironmental risks. 2.4.1 Types of geoenvironmental risk assessment models. Geoenvironmental risk assessment models are typically divided into quantitative and qualitative models, each offering different approaches for evaluating risks associated with geoenvironmental issues. These models assess both the likelihood of an environmental hazard occurring and the severity of its potential impact. 2.4.1.1 Qualitative risk assessment models. Qualitative models are used to provide an initial evaluation of geoenvironmental risks based on expert judgment and a series of predefined criteria. These models are often used in the early stages of project development when detailed data may not be available or when a rapid assessment is required. Risk matrix. The most common qualitative model is the risk matrix, which classifies risks according to their likelihood of occurrence and the potential impact they may have. Risks are categorized into low, medium, or high categories to facilitate prioritization and decision-making. Hazard identification and ranking. This process involves identifying potential hazards, such as soil contamination or groundwater pollution, and ranking them according to their significance. The risk is then assessed based on the nature of the hazard and its potential consequences on the environment and human health. Expert judgment. In cases where quantitative data is limited, expert judgment may be used to assess the potential risks based on past experiences and best practices. 2.4.1.2 Quantitative risk assessment models. Quantitative risk assessment models use numerical data and statistical analysis to evaluate geoenvironmental risks more rigorously. These models are particularly useful when detailed data is available, such as site-specific soil properties, groundwater conditions, and historical data. Probability models. These models assess the likelihood of a hazard occurring over time, often by analyzing past data, monitoring results, and historical trends. For example, statistical models can be used to estimate the probability of groundwater contamination from leachates in landfills or to predict soil stability in seismic zones. Risk quantification models. These models calculate the potential severity of an environmental hazard based on its impact on the environment, public health, and economic factors. For example, in groundwater contamination, the concentration of contaminants and the time it would take for the contamination to spread through aquifers can be quantified. Monte Carlo simulation. A widely used quantitative tool, Monte Carlo simulations allow for the incorporation of uncertainty into risk models by running simulations with varying input parameters, e.g., soil permeability, contaminant concentrations, rainfall patterns. This method provides a range of potential outcomes and their probabilities. Dose-response models. These models evaluate the potential health impacts of exposure to hazardous substances by examining the relationship between exposure levels, dose, and the severity of the healthy X response. These models are commonly used in the risk assessment of soil and groundwater contamination. 12.4.1.3 Integrated Risk Assessment Models. Integrated models combine qualitative and quantitative approaches to provide a comprehensive risk assessment. These models are designed to evaluate the environmental and health risks from a holistic perspective, incorporating various factors such as site-specific conditions, regulatory guidelines, and socioeconomic considerations. Environmental fate and transport models. These models are used to predict the movement of contaminants in the environment, such as soil and groundwater. They integrate factors such as soil properties, hydrogeology, and the physical and chemical properties of contaminants to assess their potential for migration and impact on the surrounding environment. Geospatial risk models. Geographic Information System (GIS) based models are used to visualize and analyze risk data in spatial formats. These models help identify areas with high contamination potential, potential pathways for contaminant transport, and vulnerable populations that may be impacted. Life Cycle Assessment LCA is an integrated risk assessment approach that considers the entire life cycle of a geotechnical project, including its environmental impacts from construction to decommissioning. This model helps assess long-term risks and identify sustainable solutions for managing geoenvironmental hazards. 2.4.2 Applications of Geoenvironmental Risk Assessment Models. Geoenvironmental risk assessment models are applied in a variety of contexts, including site investigations, regulatory compliance, land reclamation, and environmental impact assessments. Some common applications include 2.4.2.1 Soil Contamination Risk Assessment. Risk assessment models are widely used in evaluating the potential risks associated with contaminated sites. These models assess the severity of contamination, the extent of soil and groundwater pollution, and the potential pathways for human exposure. Site characterization. Risk models help identify and characterize contaminants, their sources, and the pathways through which they might spread. The models assist in determining the need for remediation or mitigation measures. Remediation design. Quantitative risk models help to develop remediation strategies by identifying the most effective methods for reducing or eliminating contamination. These models may be used to select treatment options such as soil excavation, in situ stabilization, or bioremediation. 12.4.2.2 Groundwater Pollution Risk Assessment. Groundwater is a critical resource, and its contamination can have significant environmental and public health consequences. Geoenvironmental risk assessment. Models are essential for predicting and evaluating the risk of groundwater contamination from various sources, such as landfills, industrial waste sites, and agricultural runoff. Plume migration modeling. Models are used to predict the movement of contaminants through the soil and groundwater. This allows for an evaluation of the extent of contamination and the identification of affected areas, helping to develop strategies for containment or remediation. Aquifer vulnerability. Risk models assess the vulnerability of aquifers to contamination, taking into account factors such as soil permeability, hydrological conditions, and the presence of protective barriers. 12.4.2.3 Waste disposal risk assessment. Waste disposal is a major concern in geoenvironmental engineering, particularly when hazardous materials are involved. Risk assessment models are used to evaluate the potential impacts of waste disposal on the environment, focusing on issues such as leachate formation, groundwater contamination, and air quality. Landfill design and management. Models are used in the design of landfills and waste containment systems to assess the risks of contamination, evaluate liner performance, and monitor leachate migration. These models help ensure that waste disposal practices meet environmental regulations. Leachate prediction and management. Leachate modeling is crucial for predicting the release of pollutants from waste disposal sites and for designing systems to control and treat leachate. Risk assessment models are used to assess the potential for leachate contamination of surrounding soil and groundwater. 12.4.2.4 Risk-based decision-making for environmental remediation. Geoenvironmental risk assessment models are often employed in risk-based decision-making processes for site remediation and environmental management. These models help determine the priority of remediation activities based on factors such as the severity of contamination, risk to human health, and environmental sensitivity. Cost-benefit analysis. Risk models are used to evaluate the cost-effectiveness of different remediation strategies, considering both environmental benefits and financial costs. This approach helps prioritize remediation efforts for sites with the highest potential risk. 12.4.3 Conclusion. Geoenvironmental risk assessment models play a critical role in understanding, managing, and mitigating the environmental risks associated with geotechnical and environmental hazards. By using qualitative, quantitative, and integrated models, professionals can assess potential risks, predict the environmental impacts of projects, and develop strategies to prevent or mitigate adverse EX. These models help ensure that geotechnical projects are conducted in an environmentally responsible manner, protecting both human health and the surrounding ecosystems. Chapter 12: Geoenvironmental Engineering. 12.5 Sustainable Practices in Geoenvironmental Engineering. Sustainability in geoenvironmental engineering is crucial for minimizing the negative impacts of geotechnical projects on the environment and ensuring that natural resources are used responsibly. Sustainable practices focus on optimizing the use of land, minimizing waste and pollution, and reducing the consumption of resources while maintaining or enhancing the functionality of geotechnical systems. This section explores sustainable practices in geoenvironmental engineering, including strategies for waste management, pollution control, resource conservation, and the development of green technologies. 2.5.1 Sustainable Waste Management Practices. Waste generation is an inevitable byproduct of many geotechnical and construction activities. Sustainable waste management aims to reduce waste generation, promote recycling and reuse, and minimize the impact of disposal on the environment. Sustainable waste management practices in geoenvironmental engineering focus on responsible handling, treatment, and disposal of waste materials. 2.5.1.1 Waste minimization. Designing for reuse and recycling. In many geotechnical projects, materials like soil, rock, and concrete can be recycled and reused. Sustainable practices encourage designing projects with recycling in mind, such as reusing excavated soil, infill or backfill applications, or using recycled aggregates in concrete mixes. On-site waste processing. Instead of transporting waste to site, waste processing methods such as sorting, crushing, and screening can be applied on-site. This reduces transportation costs and environmental impact while making materials available for reuse. 2.5.1.2 Waste-to-energy solutions. Bioremediation. For sites contaminated with organic waste, bioremediation techniques can break down hazardous substances into less harmful compounds. This reduces the volume of hazardous waste and minimizes the need for costly disposal methods like landfilling. Waste-to-energy systems. In some cases, waste materials like biomass, landfill gas, and organic materials can be used to generate energy. This provides an environmentally friendly alternative to traditional waste disposal. 2.5.2 Pollution control and remediation technologies. Pollution control is an essential component of sustainable geoenvironmental practices. Minimizing and mitigating contamination from soil, groundwater, and air contributes to the protection of human health and the natural environment. Geoenvironmental engineering focuses on both preventing pollution and addressing existing contamination. 12.5.2.1 Sustainable soil remediation. In situ remediation. Instead of removing contaminated soil, in situ techniques. Treat contaminants on site, reducing the need for excavation and transportation. Methods like phytoremediation, using plants to remove contaminants, and bioremediation, using microorganisms to degrade pollutants, are environmentally friendly options for soil cleanup. Electrokinetic remediation. This technique uses electric fields to mobilize contaminants in the soil and facilitate their removal or degradation. It can be used for fine-grained soils and is less disruptive to the surrounding environment than traditional excavation-based methods. 12.5.2.2 Groundwater treatment. Natural attenuation. In some cases, contaminated groundwater can be left to naturally recover over time as microorganisms in the soil break down pollutants. This approach is cost-effective and requires minimal intervention, but it may only be suitable for certain contaminants and site conditions. Sustainable groundwater remediation systems, pump and treat systems, when necessary, can be designed to use renewable energy sources like solar or wind power, reducing the carbon footprint of the remediation process. 12.5.2.3 Pollution prevention. Green engineering practices. Sustainable pollution control emphasizes the use of green technologies and best practices that prevent pollution from occurring in the first place. This includes designing systems that minimize the generation of pollutants and using environmentally friendly materials that are less likely to cause contamination. Green infrastructure for stormwater management, sustainable urban drainage systems, SUDs, and green infrastructure such as rain gardens, permeable pavements, and vegetated swales reduce the amount of runoff and minimize the risk of water pollution. 12.5.3 Resource conservation and efficiency. Sustainable geoenvironmental practices focus on conserving natural resources, optimizing their use, and reducing the environmental impact of resource extraction and consumption. By adopting energy-efficient methods and technologies, geotechnical engineers can help reduce the carbon footprint of construction activities. 12.5.3.1 Energy-efficient construction. Use of renewable energy, incorporating renewable energy sources such as solar, wind, and geothermal energy into geotechnical projects can reduce the consumption of fossil fuels and lower greenhouse gas emissions. For example, solar panels may be used to power equipment and machinery on site. Energy-efficient design. Sustainable construction practices emphasize energy-efficient design principles. Geotechnical engineers can contribute by optimizing soil compaction, reducing heat islands, and using energy efficient materials. 12.5.3.2 Sustainable Material Selection. Low carbon materials. Choosing materials that are sustainable and have a low carbon footprint can significantly reduce the environmental impact of geotechnical projects. For example, recycled concrete, fly ash, and slag can be used in concrete mixes to lower the carbon emissions associated with cement production. Locally sourced materials. Using locally sourced materials reduces the need for transportation, which in turn reduces fuel consumption and greenhouse gas emissions. It also supports the local economy and minimizes environmental disruption. 2.5.4 Green Technologies in Geoenvironmental Engineering. Incorporating green technologies into geotechnical engineering practices is key to achieving sustainable development. These technologies help to minimize the environmental impact of projects, optimize resource use, and promote the long-term health of the ecosystem. 2.5.4.1 Geothermal Energy Systems. Geothermal energy is an underutilized renewable energy source that can be integrated into geotechnical engineering projects. Ground source heat pumps, GSHP, use the Earth's constant temperature to heat and cool buildings, reducing the reliance on fossil fuels for temperature control. Sustainable heating and cooling. GSHP systems can be used in foundation design, reducing the environmental impact of traditional heating and cooling systems. This system is energy efficient and provides long-term cost savings while minimizing environmental harm. 2.5.4.2 Carbon Capture and Sequestration CCS. Geotechnical support for CCS. Carbon capture and sequestration is an emerging technology used to capture and store carbon dioxide, CO2, emissions from industrial processes. Geotechnical engineers are involved in designing safe, long-term storage sites for CO2, typically deep underground in depleted oil and gas reservoirs or deep saline aquifers. Geoengineering for climate change mitigation. Geoengineering solutions such as enhanced weathering and biochar sequestration can help sequester carbon in soils and other geotechnical systems, reducing the atmospheric concentration of CO2 and mitigating climate change. 2.5.4.3 Renewable Energy Foundations. Wind and solar energy foundations. Geotechnical engineering plays an essential role in the design of foundations for renewable energy structures such as wind turbines and solar panel arrays. These structures require specialized foundation designs that take into account local soil conditions, load-bearing capacity, and environmental factors. Sustainable offshore energy foundations. In offshore wind energy projects, geotechnical engineering solutions are used to design foundations that can withstand harsh marine environments, techniques such as monopile foundations and suction bucket foundations minimize the environmental footprint of offshore energy projects. 2.5.5 Conclusion. Sustainable practices in geoenvironmental engineering are essential for promoting environmental stewardship and ensuring that geotechnical projects contribute positively to the long-term well-being of the planet. By focusing on waste reduction, pollution control, resource conservation, and the integration of green technologies, geoenvironmental engineers can help create more sustainable, efficient, and environmentally friendly infrastructure. The adoption of these practices is not only critical for the environment, but also supports the economic and social goals of sustainable development. Thank you for your attention in watching this video lecture on the Triune Biblical University Global Extension USA channel. Kindly like, share, subscribe, and comment to help us bring more educational content your way. The link to the next part of this video will be posted in the description section.